hosting the webinar today. So if you have any questions, feel free to type them into the question box on your panel, and then I will ask Kurt, our presenter, those questions after the presentation today. So as a reminder, if you want to view our webinar schedule, you can go to obcinet.org. And also there you can actually go and click on the links to the previous webinars we have and see the recordings for those webinars. And today's webinar will be recorded and put onto the obcinet.org website as well. On to today's presentation. Kurt Wagner is a fisheries biologist with the Ohio Division of Wildlife in the District 3 office in Northeast Ohio. He graduated from Penn State University with a bachelor's degree in wildlife and fisheries, and then spent time at the University of Illinois at Urbana-Champaign pursuing his graduate studies with Dr. Wall at the Illinois Natural History Survey. Among Kurt's primary responsibilities with the Ohio Division of Wildlife in District 3 are to monitor streams and river fish populations and represent the Ohio Division of Wildlife at numerous watershed, stream conservation, and angling organizations. Included in his broad array of stream responsibility is his involvement with the state's brown trout program, the focus of today's presentation. So now let me hand it over to Kurt, and he'll go ahead and continue with the presentation. Thanks, Kurt.
All right, thank you, Ken. Ken, you can hear me, correct?
Yep.
Okay. Well, good morning, everybody. I appreciate this chance to present some work that we're excited about for everyone. It's the first time I've done this kind of format, so it's interesting. Hopefully everybody has smiling faces, but I guess if you're sleeping, at least I won't be able to see that like you can when you're actually presenting. My screen just changed. I'm sorry, folks. Am I full screen for people? There we go. Okay. The work I'm going to talk about today is a project that we at the Division of Wildlife began in 2010, scoping it out, and actually did field work 2011 through 2014. As Ken said, I'm one of the fish biologists up at our District 3 Akron office. Co-author on this talk, Joe Conroy, is one of our research biologists at our Inland Fisheries Research Unit. A little bit about how the Division of Wildlife's fish management section is structured. Our specific targeted research projects come out of that shop, the Inland Fisheries Research Unit, and then representatives from the various districts team up with the IFRI folks to actually execute the project. So Joe Conroy has had a very critical role in seeing this project through. So one of the guiding principles of the Division of Wildlife is to improve opportunities for fish and wildlife recreation. And as fisheries professionals, part of what that means is seeking to identify ways to provide, for a diverse array of species for anglers to fish for and habitats for them to pursue those fish in. So providing for anglers the chance to pursue inland trout, specifically in streams, is just one small avenue in which we can sort of carry out one of those fundamental principles that the Division of Wildlife holds. So that's what we're going to talk about today, is some of the challenges for providing a trout fishery in Ohio, and this study aimed at understanding it more so we can sort of provide the best product for our Ohio anglers. For those listening within the division and you're interested, this is Project FIDR 17. For those not in the division, I guess that's just a series of random numbers. So our roadmap today, we'll just begin with a little bit of overview of the history of the brown trout program in Ohio and some of the challenges and threats that we know exist right out of the gate for providing this fishery. We'll transition then into sort of the nuts and bolts of the study, going through what we measured, how we did it, what we learned from it, and then just touch on where we're at now and where we think we may go moving forward with possible adaptations to the brown trout program. So to understand the background of Ohio's brown trout program, and really the premise underlying this current study, we need to first understand a little bit about the physiology of brown trout, because that's going to be critical to some of the stresses that we know we have in carrying out this program. Like most salmonids, brown trout are fairly sensitive to warm water. And we know now, and we even knew at the inception of beginning the brown trout program, that heat will likely be a challenge and may limit the success of brown trout in Ohio. And really the question is, to what extent? Like I said, the vast majority of fishes, their various physiological rates, consumption, metabolism, etc., are directly related by the surrounding environment that they reside in, specifically temperature. And brown trout, as all fish go, have a fairly restricting thermal limits in relation to the temperatures, especially in relation to the temperatures that Ohio has available in our aquatic systems. So these limits, they really are best quantified in the laboratory. And so some prior studies have taken brown trout and sort of examined them across temperatures in the laboratory, and that's what helps us understand a little bit about the thermal physiology of brown trout. So this figure is just kind of showing sort of just a coarse schematic of the temperature ranges that basically brown trout like and don't like, let's say. The optimum growth occurs from about the 40s through the mid-60s. But the trials show that, they certainly can feed, which is an indication of not being stressed. They can feed all the way from the mid-30s up into the upper 60s. So through the 70s and up into the 80s, that's when brown trout started exhibiting stress, and that's inferred by both observations of behavioral changes and also physiochemical changes within the body that indicate stress. And then really where the rubber meets the road then, mortality due to the warm water observed, to begin in the mid-70s, and really by the time in your upper 80s, you have a complete species mortality of whatever batch of brown trout are being tested. So that's a little bit of the range of how temperatures affect the brown trout. An often used laboratory value is called the incipient lethal temperature, and it's really the water temperature at which at least 50% of the population can't survive for an indefinite amount of time. And oftentimes in the literature, a 7-day test period is sort of the norm. So, in essence, what we're looking at is, across at least 7 days, the temperature at which 50% of the brown trout or more will not survive. So for brown trout, that incipient lethal temperature, and we'll come back to this throughout the talk as sort of a benchmark to be aware of, is 76 degrees Fahrenheit, or roughly 25 degrees Celsius. So as we mentioned earlier, one of the guiding principles of the Division of Wildlife is indeed to provide recreational opportunities and diversify those angling opportunities. But you can imagine there's quite the balancing act in providing certain fisheries to Ohio anglers. In the brown trout context, first you need to consider the ecological potential across the state to begin with. What's sort of the landscape or the layout that we have to work with. And really for trout, the aquifer yield, essentially the groundwater flow, would be critical. We know that only drainages that have high and consistent groundwater flow even have the possibility of sustaining trout year-round. And on this map that you see in the upper left, those areas of higher aquifer yield are indicated in the deep blue color. So additionally, angler demand and interest needs to be considered. What you're seeing here on this map of Ohio, the green counties represent the county of residence of anglers that identify themselves as sometimes fishing for brown trout in a recent online angler survey that the Ohio Division of Wildlife executed. And so you can see that brown trout anglers are fairly well represented geographically across the whole state. The watersheds that are in yellow, they represent the 3 current drainages in which we currently have the brown trout program in existence. So presumably, you can see that there's widespread travel to go and fish for these brown trout. So the interest certainly is there, and there would be a need or desire to try to keep those fisheries spread out and be accessible as much as possible to all anglers. Third, the Division of Wildlife hatchery system, it's in a way it's a fixed entity. It can only raise so many brown trout. without either increasing costs or decreasing the production of other species. So really, there's, what you're looking at then would be trade-offs and balances in terms of the actual numbers and sizes of brown trout that could be reared and the numbers of streams that could be stocked. And then lastly, the availability of public access needs to be considered when seeking to provide an angling opportunity for an Ohio angler. The brown trout that are raised, and all our fish that are raised, are really funded through angler dollars. So it's imperative then that these fish are then accessible to Ohio anglers to pursue. So having adequate public access is critical. We sort of arbitrarily identified at least 1 river mile as being sort of that acceptable range you would want for folks to get out and use the resource. So these 4 considerations, they create a delicate balancing act when considering strategies to provide for a new recreational opportunity, and then especially a challenging one of trying to provide brown trout fishing in Ohio. Now, back in the early 1990s, a research project was initiated with the first objective of just identifying candidate streams in which to stock state-reared brown trout for the creation of this new fishery type. And so this endeavor in the early 90s basically considered those restraints that were mentioned in the prior slide, the access, the ecological potential, et cetera, hatchery availability. And what they came up with then was 3 candidate streams that were proposed for stocking. You have the Mad River, which is in western Ohio, the Clear Fork of the Mohican, which is in north central Ohio, and then Clear Creek, which is in south central Ohio. And these 3 streams are the ones that were ultimately chosen to be a part of sort of the new, and really as it stands now, brown trout program. So every year since 1997, at the conclusion of choosing those 3 streams, the Division of Wildlife has stocked roughly 25,000 yearling brown trout. So these will be age 1 trout coming out of the hatchery in October. Clear Creek receives 3,500 trout. Clear Fork of the Mohican is unique in that it's divided into 2 sections. There's a section of the river above Pleasant Hill Reservoir and a section below Pleasant Hill Reservoir. And they have fairly different characteristics. And for this study, we treat them as sort of separate entities in terms of data collection and analysis. Above Clear Fork gets about 7,400 trout, and below 2,600 brown trout. And then the Mad River in western Ohio receives 11,500 trout annually. These systems are currently managed with a 2-fish daily limit and a 12-inch minimum harvestable size. So that's the regulations in place on these streams currently. There are, however, some potential roadblocks that limit the success of the current brown trout program. And to a point, we know and have identified that these roadblocks exist. The challenge has been putting real numbers on them to sort of move forward with understanding of how we can get around or exploit some of these roadblocks. So the first is simply that we know temperature does threaten success. I showed the figure of brown trout physiology, and so it's not too far of a leap to realize that Ohio streams certainly could present challenges to maintaining a quality trout fishery. Second, we have little or no growth information for which to base management decisions on. And then lastly, we stock many sites, typically at road crossings, but we really don't know anything about the movement or possibly lack thereof of brown trout once they're stocked. So that brings us to this current project. This project, which is the focus of today's presentation, FIDR-17, as I said, is specifically aimed then at putting actual numbers to survival, growth, movement, in an attempt to sort of better understand these unknown qualitative threats and actually then sort of put quantitative understanding on those threats. So let's dig into the actual meat and potatoes here. Like I said earlier, for a time reference, the actual field sampling component as we walk through these 3 approaches and measurements. The temporal scale here is from the summer of 2011 through the end of summer 2014. So we've just wrapped up our field component of this project across 4 summers. So Survival of stock brown trout was assessed using 2 annual surveys. Each survey consisted of between 10 and 20 sites per stream, and a site was considered 0.1 river miles. So, like I said, it's 2 assessments. The first one we termed pre-summer. Really, I think probably the folks at our research unit called it pre-summer just because they didn't want us to be scared by calling it winter. We actually did these, quote, pre-summer assessments in February or March, so it was still very cold, still certainly winter, and the idea was to assess the survival and distribution of brown trout following that prior October stocking, and well before there's any chance of heat, thermal threats to have affected brown trout survival, movement, etc. Then the second assessment was summer, really post-summer assessment. We would do this in late August, and it would be after, the maximum heat threats would have been experienced by brown trout in the system. You can see from the picture, the gear we used was electrofishing gear. It's a barge-mounted DC electrofisher, and so you have 2 anodes, and it's used by weighting. There's a few sections of the Mad River where we had to use a small electrofishing John boat, but otherwise, all the data were collected using this barge electrofishing apparatus. So the index of survival is relative abundance. Like a lot of fisheries work or natural resources work, you don't really measure true numbers in a population. So instead, you have an index as a surrogate for the true numbers that exist out there. So in this case, it's catch per unit effort, or even sort of more intuitively, we could look at it as the number of brown trout caught per hour of electrofishing. So that's going to be the metric that we use throughout the next few slides. And then further, this survival was placed within the context of ambient stream temperatures. And so in each of the streams, we had at least 6 temperature loggers deployed across the longitudinal gradient of the stream. These were maintained about a foot above the bottom. What each logger did was record a temperature reading every 30 minutes throughout the entire duration of the study. So as you can imagine, we obtained, a wealth of temperature information that we needed to sort of distill down into manageable values. And we would go out and download these loggers every so often throughout the study just to make sure they were present and operational. So, as I mentioned, the brown trout survival was approximated using this estimated relative effort, or relative abundance, I should say. And that's what we're going to look at here on the y-axis of the figure. On the x-axis, we have the sampling season. So SU11 would be summer 2011. WI12 would be winter 2012. So that would be our pre-summer assessment that I mentioned earlier, and then so on along the x-axis. So this is going to be sort of the pattern of the figure that the next few slides will hold to. The data points are going to be indicated in either red or blue to, again, just help you cue on whether that was a summer or a winter assessment. And then here we're going to start by building the figure for Clear Creek. And so what you're looking at is the 4 estimates of relative abundance from Clear Creek from the summer surveys, so summer 11, 12, 13, and 14. And you can see that there's a fair amount of variability across years. So now we're adding in the relative abundances from the winter surveys, again for Clear Creek. And you can see that they're higher, and you recall that we stocked trout in October. And so you look at the difference from summer 2011 to winter 12, or summer 12 to winter 13, you see that bump up that would presumably be due to the recent addition of stock trout. Next, we see differences across years in terms of how heat likely is affecting the population. Summer 2012 was a very hot year, and you can see between our winter 2012, let me use the pointer here, between our winter 2012 value from our survey to that following late August, the summer survey, a drastic decline to almost 0 fish in the system, presumably due to hot weather, which we'll get to that in a little bit in terms of how we can really try to tease out that relationship. But then fast forward to the span here for the summer of 2013 and the span of summer in 2014, both comparatively cool summers, and we see very little variation in our measure of relative abundance between our winter and summer survey. So as a whole, this is sort of one example here in Clear Creek where we see how, depending on the summer, it may really affect number of trout that remain in the stream after the summer. So here on this slide, all I did is slide that same exact data set, Clear Creek, slide it to the left so that we can now look at the other streams on the same slide. So first, here's Clear Fork above Pleasant Hill. That's the second panel in from the left. And you see a fairly predictable cyclic pattern here between summer and winter survey results. But interestingly, it's sort of counterintuitive to what I just described with Clear Creek in terms of how summer affects trout abundance. What we're seeing here is each summer having the higher abundances than the corresponding winter survey. And really, I think what you're seeing here is a little bit of the sort of devil in the details of the data. This section above Pleasant Hill in particular was extremely difficult to sample in winter, and I think all the researchers involved would agree that we're pretty sure we had quite the low bias in terms of our catch rates and catch numbers during our winter surveys due to the high flows in that system, especially in February and March. So take that what it is. A lot of the rest of the analysis for today is going to focus on those summer assessments anyways, and the summer flows were much more manageable, and we feel a lot more confident in the summer estimates for that section of stream. Next, we'll build in here Clear Fork below Pleasant Hill. So this is about a 5 river mile stretch below the Pleasant Hill Dam that's really entirely through public access. It's a beautiful stretch. I'm sure a lot of you have been there and visited it. So what we're seeing here is kind of matches the pattern with Clear Creek. We see in situations like summer 2012, and summer 2011, by the way, was also a very hot summer. We don't have the winter data to correspond with it, but as we went in August in 2011 and August in 2012, following 2 hot summers, we caught no brown trout. Then compare that to summer of 13 and summer of 14, mild summers, temperature-wise, and basically, based on our catch per hour estimates, have about the same standing stock of brown trout in there in the summer as you did that same year in the winter. So again, sort of indicating the role the heat plays in structuring the survival of brown trout. Then lastly, we'll pull in the Mad River. The Mad River routinely had high relative abundance estimates across seasons and years. So it's sort of the one you can always count on to have good numbers. So let's shade out the winter data points and just look at our summer assessments. And you see there's a lot of variation among streams, even within a stream among years. For example, we have a high of nearly 40 fish an hour from the Mad, and then we have a handful of 0 or near 0 fish per hour estimates from other streams in certain years. So the question becomes sort of obvious, is can we relate summer stream temperature to the post-summer relative abundance estimates? In other words, does the data suggest that stream temperature can predict brown trout survival over summer? So we can use our temperature logger data and actually calculate the number of July days. So this is what's on the x-axis here. Calculate the number of July days that had a maximum observed temperature greater than 24.7. So you'll recall that 24.7 Celsius, that's that incipient lethal temperature that I brought up at the beginning of the talk in terms of that temperature where 50% or more of the population died after 7 days exposure. So that's sort of where we get this bizarre metric of July days greater than that temperature. And what we can do then is we can plot that temperature for each stream and year and survey. We can plot that against the catch per hour estimates from each survey. Again, you can reference the streams by the shape, square, triangles, circles, and then the individual years will be color-coded to try to keep all this data straight on one figure. So first, I placed in the 2011 data, and that year we had a range of about 20 fish per hour from the Mad River, all the way down to 0 fish per hour in Clear Fork below Pleasant Hill. Next, we'll bring in the 2012 data in black, and that was a hot summer, and you can see that 3 out of the 4 systems had over 20 days in July with a maximum temperature over that incipient lethal temperature value. green, 2011 or 13, I should say. I added that one in. That was a fairly cool year, as I mentioned. None of the systems even had 5 days that were above that incipient lethal temperature, and relatively speaking, you can see fairly high catch rates as well from those summer surveys. And then lastly, in blue, 2014 data is plotted in. Again, a fairly cool year with really only Clear Fork below Pleasant Hill having sort of a concerning number of July days above that incipient lethal temperature. But even so, still having a reasonable catch rate from our most recent summer survey. You can note again that the Mad River never had any July days that approached or exceeded that 24.7 degree mark. So what we can do, we can take this data and we can fit a linear function to it. You know, we could all look at it and argue different functions you could fit, but just for simplicity's sake here, fit a linear function to it. In fact, you get a p-value for those interested of 0.002. So you do get a fairly convincing linear fit. And really beginning at the y-intercept, which is roughly 22 fish an hour, for each additional day in July that exceeds that incipient lethal temperature, you decrease your catch rate by about 3/4 of a trout. So I mean, I'm trying to sort of annotate what the linear function is, but just to give you a rate of decrease, you know, each day you're over that temperature, you're almost losing another trout out of your catch per effort estimate. So certainly there's indication that those July temperatures directly relate anyways to their survival, essentially the abundance of brown trout. You know, another way we can do that, we can push the same data through a two-dimensional Kolmogorov-Smirnov test. It's a big word test, but basically it's taking data and trying to find a logical threshold using sort of the math behind the scenes. And what that test did is basically identified a threshold right at 7 days where it sort of maximized the difference between the catch per effort estimates on the left side of that threshold versus the catch per effort estimates on the right side of this threshold. And so it's interesting. I mean, this is just a statistical model, statistical test that came up with this 7-day threshold, and go figure that 7-day threshold is exactly the same time frame that this incipient lethal temperature was identified using. And so how this threshold breaks down is cooler than that, fewer than 7 days above the incipient lethal, you're averaging 22.6 fish an hour. The average for 7 or more than 7 days above that incipient lethal temperature, your average abundance goes down to only about 6 fish per hour. So really, you know, biologically speaking, really identifying a threshold here in the amount of hot days in July that these populations can really withstand, essentially. So I wanted to point out the 3 data points in the box. These are the data points that I just made yellow and put a rectangle around. They look like somewhat outliers. They're all from the Clear Fork system, the Clear Fork of the Mohican system. And really, I think what you're seeing here is the potential of this system in particular to have a widely distributed thermal refugia. Locals in the area often speak of in-stream spraying seeps that might add cool water. And our data over those assessments, really that data is full of sites with few or no fish, and then you have a handful of 0.1 river mile sites where you have quite high abundances, even approaching like 40 fish an hour. And so I think in some of these years here, what you're seeing in the Clear Fork of the Mohican is, you know, across the board, heat really affecting the trout, but yet at a few places, those trout finding and stacking into some cool patches, essentially, some thermal protection. So that's kind of what's going on. We think with those points, you know, like specifically this point that I'm circling, that summer had quite high temperatures, but still reasonable catch rates. So to summarize the survival component of this study, it's not terribly surprising, but we certainly documented that summer survival, which is quite variable, seems to relate to ambient summer temperatures. So hot summer, lower survival, at least in some systems. And so now, you know, you can see where we're moving towards actually having real numbers and some predictive power to relate stream temperature to the expected survival of brown trout. Further, we can see how the stocking supplements the loss due to summer mortality. And that in some instances, brown trout are only abundant from October post-stocking through the beginning of summer, let's say, but still provide for seasonal angling opportunities even in some of those hot summers like Clear Fork below Pleasant Hill, where the hot summers pretty much wiped out the trout. You have at least 6 months or so of opportunity for anglers. So let's move into the growth portion of the study. Most specifically, we wanted to determine the amount of time in a stream system it was taking our stock yearling trout to reach harvestable size. I think I mentioned earlier that these fisheries currently are regulated with a 12-inch minimum size for harvest, and so we'll be using that 12 inches as sort of a benchmark and seeing how long it takes fish to even attain those sizes. So first, in the hatchery, in October, as these fish are about ready to be stocked out each year, we went in and measured the length of a subset of each stocking group. So basically, a stocking group would be a batch of fish that are destined for a specific stocking site within a certain stream in that given year. And so we really tried to get a handle on the average length of all those fish going out of the hatchery each year. Each fish which I'll talk about a little bit more in a minute, but each fish were batch marked with one or more magnetized wire tags in specific body locations on the fish to identify the stocking year and also the location they were stocked at within the stream. So then at each successive field sampling event, those winter and summer assessments I mentioned, we measure the length of all the fish we capture, and that gives us the ability then to sort of track at least a batch or a cohort's growth pattern across time. So we'll examine growth by plotting the number of days post-stocking here on the x-axis, and then the mean length in inches on the y-axis, and of course 0, the first dot for each cohort we track, will be that mean length at stocking. Again, the streams will be identified in the legend by shape, and just for sort of example's sake, because almost all the year's cohorts follow a pretty similar pattern stream to stream, we'll just look at the 2011 stocking year class. Again, I put that dashed line on just to show you the 12-inch mark again, which is that minimum size for legal harvest. And we would expect to see data that kind of match this hypothetical pattern. Some roughly linear growth trend over time, and eventually, X number of days out, reaching that 12-inch mark. So first, we'll plot that circle there. That's the Mad River 2011 stocking, and right about 8 inches. That was the average size of those fish when they left the hatchery. Next, I put in the mean length measured from the winter 2012, so that would be that winter just following that October 2011 stocking. You can see a little bit of growth here again, only as indicated by sort of the mean length of all the fish of that age that we sampled. And then there's the rest of the assessments all the way out through 2014, I believe, that the last data point represents. And you could fit, as expected, it fits a roughly linear growth pattern. And when you actually model that out, that predicts taking nearly 2 years for 2011 stocked fish in the Mad River to actually attain that 12-inch mark. Next, the triangles. That's the Clear Fork above Pleasant Hill. You plot a line and extrapolate out on that one, and you're looking at nearly 2.5 years for fish in that cohort to reach that 12-inch mean length. We'll shade those out. Now we'll look at squares, Clear Creek, and upside-down triangles, Clear Fork below Pleasant Hill. And in those two situations, you'll recall that those were the systems where we saw quite a bit of thermal stress on some years, so the fish were certainly susceptible to that mortality due to heat. We never had long-term enough survival of a cohort to actually be able to estimate days until 12 inches. So growth along with survival in these systems is quite negligible. So again, I said I'm only going to show this pattern for the 2012 stocking class, but the patterns pretty much hold true for the 2012-13 stocking cohorts as well. In addition to determining the time it takes to reach the harvestable size of 12 inches, we also want to determine the proportion of the standing population at any one moment of time within these streams that was currently at harvestable size. So just a different way of looking at the sizes of fish available for anglers in the system. As mentioned earlier, we measured the length of each fish that we caught during all of our field assessments. And in addition, we checked for the presence of those tiny magnetized wire tags I talked about, which would inform us of the age of each fish, so that we truly are lumping these fish into the right age categories as we look at the data. So we can look at length distribution data by plotting trout length here on the x-axis in inches, and then just plotting the absolute number of trout sampled on the y-axis. So again, for example's sake, I'll show you the 2012 Mad River summer survey data. So this data here in black, this represents the full complement of trout that were sampled in the Mad River during that summer assessment. Again, I'm going to put the dashed line on there. That's just representing 12 inches, that minimum size for harvest. And you can see that about 39% of the fish in the standing population in that moment for that survey period were of legal harvestable size. And really, in our opinion, and it comes down to an opinion, but to us that seems like an acceptable proportion to have, at that size or higher. What we can do, we can divide this whole group of fish in the black, we can divide that into age 2 fish. That would be fish that were stocked that prior October, or we could look at fish that were non-age 2. So in that case, it would solely be older fish, because there's no younger fish in the system since they're stocked out at age 1. And so what we have here, that same data set, but now red represents age 2 fish, and the gray represents older than age 2, essentially. And what you see here is you only have about 3, really 1% of those age 2 trout, basically almost a year after stocking, that reach that 12-inch threshold. So really all of those fish that are out there, harvestable size or larger, are older than the age 2 batch. So we can take this now and we can summarize the whole study's worth of data in sort of a tabular form, so it's easier for you to look at it all at once. So we have across the top in the green are just the years and the specific seasons of the assessment, the summer assessment, winter, summer, winter, and the actual data in the box is going to be the percent of harvestable fish in that system during that given survey. The cells will be color-coded, with green being what we consider acceptable or a fairly high proportion that are above harvestable size, all the way down through black, which would be a very low proportion of fish in the population that are 12 inches or larger. So what I did here is I put the 39. That's 39%. That matches this exact 39% that we just showed you a bit ago here. So you can have a frame of reference of how this data is fitting together. There's that 39 from the Mad River Summer 2012 survey. So now let's build the rest of the table. We have Clear Creek. That's the one that's sitting just southeast of Columbus there. You can see pretty much across the board on all of our surveys, we rarely and usually never had any fish in the population that were 12 inches or higher. Clear Fork above Pleasant Hill, we generally saw an intermediate proportion of the population that was at or above 12 inches. Clear Fork below Pleasant Hill, much like Clear Creek, is also one of the systems that are thermally stressed in the summer, as we showed earlier. And we see the one exception just being actually this past summer, 2014, but really otherwise, really almost no legal fish in the system during any of our survey work. And then lastly, the Mad River. That's the one that consistently has a comparatively high proportion of the population that's at or above that 12-inch mark. So to summarize the growth side of the study, you can see that few trout really ever reach harvestable length. Trout, as a rule, are going to need to survive between 1 and even over 3 years, an average of about 2 years across the systems to attain that 12-inch size. And like I said, the majority of them never reach that, due both to slow growth as it is, as well as fairly high system by system or year by year mortality rates. So lastly, let's take just a brief look at movement patterns. We're not going to spend a lot of time on this side of things. Of most interest to us really was whether stocked brown trout leave their stocking location or rather just hang around roughly where they were stocked. I mentioned earlier that the stocked fish were tagged with tiny magnetized wire tags. For those that are familiar with coded wire tags, these are essentially that tag just without the code. So we're not looking to kill the fish, dig the tag out for an individual mark. Rather, the tiny tag allows a magnet, basically a magnet wand, to very accurately pinpoint where within the fish's body that little tag is placed. And so the fish's body is actually what's helping us sort of batch mark and differentiate these fish. So body locations included the dorsal, caudal, pelvic, and pectoral areas of the fish to receive the implant tag, and that was really dependent on stocking location. In addition, a snout tag was given on alternating years in order to then be able to actually tease apart the age classes when we were out in the field. So trout were then stocked across the upstream downstream gradient in each stream, with fish from a given stocking location having the different body tag, kind of like the schematic shows here. So we can know that, okay, a fish that we have in hand during sampling with a dorsal tag was originally stocked in that upstream section of that particular stream in question. And then what that allows us to do, really, as we go in and do our assessments, we can see, where these fish are from. Are they moving around the stream? Are they roughly in the same neighborhood as where they were originally stocked? And really the short story of this is sort of a classic biologist answer of yes and no. Trout stay and move. And really what I mean by that is we found across the whole study and across the 4 different study streams that brown trout were 4 times more likely to stay in the general vicinity of stocking than they were to move throughout the stream. And then further, those that did move, they were again 4 times more likely to move upstream. So basically, if movement was going to occur, which was fairly rare, it was quite generally in an upstream direction rather than downstream. So, you can tell just by this figure that, this isn't the same scale of movement information that you would get if you, say, tagged fish with an individual identifying tag and then looked at individual movement rates. That's not really what we were getting at. We were sort of most concerned of, hey, are we putting fish in these couple-mile section of a stream, and we go back in, and we never see them in that section again. They all move down here or up there. That was sort of the scale that we were looking to understand in terms of movement. And really, we didn't see that being the case. By and large, fish stayed roughly within a handful of river miles of where you initially stocked them out at. So let's sort of summarize the project as a whole, and then we can talk about sort of where we see this heading in the future. From a survival standpoint, showed pretty strongly that temperature directly, I'd say, affected or at least related to brown trout survival. Certainly there's the caveat that this wasn't a mechanistic or manipulative experiment for true cause and effect, but I think the combined understanding of the physiology of brown trout with the connection in our field data of stream temperature and survival strongly argues the case that that stream temperature is our main driver of trout survival in these systems. Secondly, we see that by and large trout grow very slowly in our Ohio streams. Few, if ever, really reach the current legal harvestable size of 12 inches. Those that do, it takes a long time for them to get there, pretty near 2 years to attain that 12-inch size. And lastly, as a general rule of thumb, brown trout are not showing high movement rates throughout a given stream. For the most part, they stay in the general stocking vicinity over a couple river miles of their stocking location with the occasional larger scale upstream movement. So where does this leave us now in sort of the conclusion of our project, FIDR-17, and how we're going to manage these brown trout streams in Ohio? Right now, the team of biologists that are working on this project, we still are wrapping up certain types of the analyses to kind of get final numbers. We've been meeting together in-house as well as we maintain a close pulse formally and informally with our trout anglers to sort of hear out their thoughts and concerns. So I guess you would say we are in the sort of final analysis, final sort of decision-making phase right now. Some changes that are being considered include removing the minimum size, the minimum harvestable size limit of 12 inches, and just simply retaining the 2 fish daily limit. We're pretty confident that harvest is not at all substantial anyways, and likely would still remain low just due to the catch and release practices that most anglers that are targeting brown trout exhibit. So with how long it takes and how few fish reach that 12-inch limit, it doesn't make a whole lot of sense to keep that in place. Despite the frequent years of thermal stress, specifically in Clear Fork below Pleasant Hill and Clear Creek, we still believe that these two areas that are both very high public access still provide anglers with seasonal opportunities to pursue brown trout, even if we don't see over summer survival or cohort carryover, every year. And then lastly, the scope and sort of scale of this presentation today didn't allow me to dig much deeper into the data than I did for you, but I can tell you we are seeing some indication from certain ways to look at the growth and survival data together by age that the overall density of brown trout in these streams, especially excuse me, in the Mad River and Clear Fork above Pleasant Hill, may be too high, and the density itself may be limiting some growth and actual cohort carryover from year to year. And so sort of to this end, we plan on moving forward, experimenting a little bit with the yearly stocking densities that we actually put out in the stream, wondering specifically whether lower densities actually would improve growth rates in year class survival and ultimately provide anglers with a population having a larger average size structure with essentially the same number of fish in the system. So that's some of the things we're considering and the directions we may be headed at this point. Like I said, the data is completely in, and that's the general trends that we're seeing. So I'd like to thank you for taking your time out this morning to listen in. I've put both my contact information as well as Joe Conroy's on the screen. So if you have any specific questions on how we did certain analyses or more detailed questions on possible changes in the future, certainly feel free to contact either one of us and we could talk more directly together. I also want to recognize the folks in the bottom left corner of the screen, what we sort of fondly call our inland stream team, essentially fish management staff from across the 5 districts, along with IFRI staff that were all names listed here were quite instrumental in the implementation of this project. So if there's time that allows, Ken, I'd be happy to try to answer any questions that you would like to moderate.
Yeah, we have some time and a few questions as well. One of the questions we got early on is you focus mostly on brown trout in streams, but do we actually have brown trout in Lake Erie, or could they even live there?
Brown trout occasionally show up in Lake Erie. I'm probably not the best person in this forum to definitively talk about salmonids in Lake Erie too much. I'm just not as familiar with the different species that all the Lake Erie border states stock. And okay. Speaking for Ohio, we stock steelhead trout solely. Other Lake Erie and Great Lakes states stock a range of other salmonids, which do occasionally show up in Ohio streams. But by and large, the answer being, it's not. Lake Erie and the Lake Erie tributaries aren't on the radar to develop as brown trout fisheries. This is specifically inland focus.
Is there any thought to stocking larger fish?
Some thought was given to that idea. It really came down to a couple things. What would be the implications on the hatchery end in terms of cost, trade-off, and numbers? And then, if once those trade-offs were understood, the flip side of sort of the black box that we don't have a good read on really is our sort of dedicated brown trout anglers' desires. Would they rather just have more but smaller fish, say, below? And specifically, you would be considering those bigger fish in the systems where you're not having carryover. So Clear Fork below Pleasant Hill and Clear Creek, like I said, which are thermally stressed, you really hardly ever see carryover for those streams to get bigger fish. So those would be the context that bigger fish would be discussed in. And as it stands now, We don't really have the read that the anglers aren't pounding on our door asking for bigger fish necessarily. And like I said, in the other two streams, Clear Fork above Pleasant Hill and the Mad River, we really think that it may be some tweaking of stocking densities that could bump the size range up more so than physically planting bigger fish.
We have a few more questions. Why do you think the Mad River stays so much cooler?
I think it has a lot to do just with the underlying sort of hydrology of that watershed. I admittedly am not as familiar, being that I'm in Northeast Ohio, with the intricate details of the Mad River. For whoever might have asked that question that's listening today, Ethan Simmons, he's the first person on the list there on the screen, one of the biologists out of District 1. He has quite the handle on sort of the intricacies and ins and outs of the Mad River, and may be able to talk a little bit more about specific stream and spring inputs to that system. But yeah, the generic answer is going to be just the way its hydrology is structured, just so much cold water input.
One question is that there was a variety of smaller systems that have adequate groundwater flow to sustain brown trout. Is there anything in the works to acquire public access in those systems and justify stocking those?
Right now there's not, and a lot of it comes back to that one slide I showed with sort of the balancing act with the hydrology, the access, etc. And really, to address this question, it would be the component of hatchery limitation and capacity. We're not really situated such to just start producing more fish to add to the stream list. I mean, this admittedly is a very small niched fishery that we want to maintain, and the three systems we have are spread out geographically, so they're fairly accessible to most Ohioans with a reasonable drive time. And so as it stands now, we're looking at just what can we do on those three systems to either maintain or improve the experience that anglers have there. Certainly there are cases, Apple Creek's a case where a private entity does stock some public accessible water, of course with permission from the Division of Wildlife, with trout. So there are going to be case-by-case situations where other trout do get stocked out. But from a Division of Wildlife stocking perspective, the answer is no. We're not looking at acquiring additional stream stretches for this program.
How does the presence in smallmouth in these systems affect brown trout viability?
That's a good question, and I guess the honest biologist answer is I don't know. We haven't really examined that whatsoever. I can say that we don't see a lot of smallmouth in these three systems when we're doing our survey work. You see some, I'm most familiar with the Clear Fork and Mohican. You see some, occasionally they're nice. As far as just the actual interplay between stocked brown trout and wild native smallmouth bass, to go much further would be speculation on how they would or wouldn't influence each other. I think from a direct predation standpoint, I mean, we are stocking these fish out big enough. I mean, albeit small as a trout goes, you're still looking at an average size of 8 inches. It would take the bigger size of stream smallmouth to directly predate on those stocked brown trout. I think if there was interaction at play, it would be, is there competition for space or food resources? And really, that's just a whole different design of a study that we certainly did not undertake. That said, one of the things when these three streams were chosen originally for brown trout was the thought of, we're not going to put these on top of a system that we know is a great smallmouth fishery, even if it had the right water temperature. So, there's certainly systems throughout the state that are known for good stream smallmouth, and you would want to leave that as such rather than trying to sort of create competing attractions within the same system. So I guess not a terribly fulfilling answer, but whoever asked the smallmouth question, I guess certainly will hunt me down if you want to chat about those interactions more.
Do you think there's any reproduction occurring, especially in the Mad River, since that stays at the right temperature year-round?
I think no. You know, certainly some of the other division folks could correct me if I'm wrong, but I think we're in agreement that we don't think that's occurring. Yes, the Mad River stays the coolest, but it also, at least on paper, seems to have kind of the oddest or most inappropriate habitat otherwise for trout. It's sort of long and straight, doesn't quite have the curve and sinuosity that most traditional trout streams have. So I think maybe from a substrate and sort of a spawning habitat framework, it would be lacking despite having the certainly suitable temperatures to sustain the brown trout. So, and then just simply empirically, we did the study long enough that we probably would have started seeing, with just how much electrofishing effort we put on these systems across seasons and years, we should have seen the oddball, very small trout, or, you know, handle, you know, a noticeable number of fish that didn't have the tags that we put in it. Because, you know, by the time we got through the second half, towards the end of the study, most of the trout out there were tagged by us. The only ones that weren't were the very old individuals that were in the system before the study began. And then we were stopped tagging every fish that came out of the hatchery. So we should have found a mysterious batch of similar size untagged fish to really support natural reproduction as well.
All right, well, thank you. That's all the time we have today. So if people still have questions, contact information there is on the screen. Please contact Kurt. And Kurt, thank you for the excellent presentation today.
Very welcome. Thank you.